Take the galaxy you live in and shrink it down to the size of a football stadium. 100,000 light-years, 400 billion stars, every constellation you have ever learned the name of, all of it compressed into 100 meters of turf and terracing. On that scale, our sun would be a grain of sand somewhere out near the touchline. Now walk up into the stands and sit down. Pick any seat. The seat is bigger than the object I want to tell you about tonight. There are several hundred of them scattered through the early universe, and each one is pouring out roughly as much light as the entire stadium, out of a space you could reach around with your arms. And for 4 years now, every category astronomers have reached for to explain them has failed. So what is sitting in that seat? And what does it mean that the most powerful telescope ever built has photographed hundreds of them and still cannot say? Get comfortable, subscribe if you have not already, and stay with us, because the answer that finally emerged is not a new kind of galaxy at all, and the reason it took 4 years to find is the part that should unsettle you. Let's begin. Part 1. The Specks. In every picture. There is a picture you have almost certainly seen. It might have been on a news site or a magazine cover, or the wallpaper on somebody's phone, or projected across the wall of a museum. A black field crowded with light. Thousands of galaxies at once, some of them stretched into arcs by the gravity of the things in front of them. Some of them so small they are barely more than a coloured smudge. It is one of the most reproduced images of the last 5 years, and it is genuinely beautiful. And almost nobody who looks at it knows that scattered through it, sitting quietly among the galaxies, are several hundred objects that nobody on Earth can explain. They are small, they are red, they look like specks of dust on a lens. And for 4 years now they have been quietly taking apart some of the most confident numbers in modern astronomy. To understand why they are strange, you have to understand what the telescope that found them was built to do, because the two things are connected. The James Webb Space Telescope was designed with one central purpose, and everything about its architecture follows from that purpose. It was built to see the earliest light in the universe. Its primary mirror is 6.5 meters across, made of 18 hexagonal segments, coated in a layer of gold so thin that the total amount of gold on the whole mirror would fit in a golf ball. Those segments had to be folded up like origami to fit inside the rocket that carried them, and then unfolded in the dark, 1.5 million kilometers from anyone who could have fixed a mistake. It launched on Christmas Day 2021 and spent the following month opening itself. Behind the mirror is a sunshield roughly the size of a tennis court, made of 5 separate layers, each one about as thin as a human hair. The sunshield is not decoration. It exists because the telescope has to be cold. The side facing the sun runs at around 85 degrees Celsius. The side facing out into space, where the instruments live, sits near 40 Kelvin, which is around minus 230 degrees Celsius. That is a temperature difference of nearly 300 degrees, maintained across a few centimeters of folded plastic film, permanently for years. There is a detail about the commissioning that I find hard to stop thinking about. When the 18 mirror segments first opened, they were not a mirror. They were 18 separate mirrors, each pointing very slightly the wrong way, producing 18 separate blurry images of the same star. Getting them to behave as one surface meant nudging each segment with tiny motors that move in steps of about 10 nanometers. 10 nanometers is roughly the width of a few dozen atoms laid side by side. Engineers on the ground spent weeks making those adjustments, remotely, on a machine they would never touch again, before a single scientific photograph existed. Everything that follows in this story sits on top of that alignment. All of that engineering exists to serve one requirement. The telescope's sensors are tuned not to visible light, the kind your eyes register, but to infrared light, the kind your skin feels as warmth. And that choice was not a preference. It was forced on the designers by the structure of the universe itself. Here is the reason. Light from the very early universe has been travelling for billions of years to reach us, and while it has been travelling, the universe has been expanding. Space is not a stage that everything moves around on. Space is a thing that grows. And as it grows, the light moving through it grows with it. A wave that started out as bright ultraviolet 13 billion years ago arrives here today pulled out long and slow, well past red, deep into the infrared. This is called cosmological redshift, and it is worth being precise about what it is not. It is not the same as the sound of an ambulance dropping in pitch as it passes you. That effect happens because the ambulance is moving through the air toward you and then away from you. Cosmological redshift is different and stranger. The distant galaxy is not rushing away through space. Space is being added between you and it, continuously, everywhere, and the light in transit is stretched by the addition. Every photon that reaches us carries the record of how much space grew while it was on its way. The stretch is a timestamp. Read the stretch, and you know how long ago the light left, which means the light from the very first galaxies, the ones that formed when the universe was only a few 100 million years old, has been stretched so far that it is no longer light you could see with your eyes even in principle. It arrives as heat. Hubble, which was optimized for ultraviolet and visible wavelengths, could not have seen these objects, not because it was not sensitive enough, but because it was listening on the wrong frequencies entirely. To read the first chapter of the universe, you need an infrared telescope. That is what Webb is. So astronomers pointed it at the deep sky, and they had a clear picture in their heads of what they expected to find. They expected mess. The first galaxies should not look like the objects we see nearby. No elegant spirals with graceful arms, no smooth, featureless ellipticals. Those take billions of years of settling and merging to produce. What the models predicted for the first few 100 million years was something much rougher. Small, irregular clumps still in the middle of assembling themselves, thick with gas, lit up by stars catching fire for the very first time, and they expected all of that to look blue. The reason comes down to temperature, and it is something you can check with a gas hob. A flame is blue at its base, where it burns hottest and shades toward orange and yellow as it cools. Stars work the same way. A freshly formed massive star burns at somewhere between 20 and 50,000 Kelvin, which is many times hotter than our Sun, and it radiates toward the blue end of the spectrum accordingly. Those stars are also spectacularly short-lived. The most massive of them exhaust themselves in a few million years, which on cosmic timescales is essentially an instant. So a galaxy full of hot blue stars is not just a galaxy that contains young stars, it is a galaxy that made those stars very recently, because if it had not, they would already be gone. Blue is the calling card of youth in the cosmos. That is what astronomers went looking for, and that is largely what they found. The first deep fields came back stuffed with exactly the objects the models had promised. Thousands of small, loose, awkward, bluish galaxies, scattered across the early universe like sparks thrown off a fire. The science of cosmic dawn had its data and moved forward, and for a few months it looked like one of those rare moments where the prediction and the observation simply agree. But sitting in those same images, in almost every single one of them, was something else. It was not blue, it was not loose, it was not messy. It did not have arms or clumps or the ragged edges of a thing under construction. It was a point, a small, intensely red point of light, so compact and so sharply defined that in the raw images the objects looked less like galaxies than like pinpricks pushed through a black sheet. At first there seemed to be only a handful of them. Then, as more data arrived, more of them appeared. Then more. Nobody knew what they were. Nobody knew what they were made of, how big they were, how heavy they were, or what was making them shine. And when astronomers reached for the categories they already had, the boxes that every other object in the observable universe fits into, every single box turned out to be the wrong shape. That is where this begins. Not with an explosion, not with a signal, not with a catastrophe. With a few hundred red specks that were in the pictures the whole time, waiting for somebody to ask what they were. Part 2. 6 objects that should not fit. In December 2022, less than 6 months after the telescope began doing science, a team working on a survey called SEERS found something they could not explain. SEERS stands for Cosmic Evolution Early Release Science, and it was one of the first major programs to get time on the new instrument. Its job was straightforward in description and enormous in ambition. Point the telescope at a small patch of sky and stare for a long time, and pull back the sharpest view yet obtained of the early universe. The patch chosen sits in a region called the Extended Groth Strip, and it was picked deliberately because Hubble had already photographed it. That mattered. If Webb saw something there that Hubble had not, the comparison itself would carry information. The images came back full of galaxies exactly as expected. Thousands of them, loose and blue and busy, doing what young galaxies are supposed to do. But mixed in among them were 6 objects that behaved differently. Compact, red, sharp-edged. They did not blur out into arms or clumps at any magnification the data supported. They just sat there, small and stubbornly point-like. The team was led by Ivo Labbe at Swinburne University of Technology in Melbourne, working with collaborators across several countries, and they published what they had found in the journal Nature on the 22nd of February, 2023. The title of the paper is a mouthful, and it is worth hearing in full because it turns out that one word in it matters more than all the rest. A population of red candidate massive galaxies approximately 600 million years after the Big Bang. 6 objects, sitting at redshifts between 7.4 and 9.1. Translate those numbers out of the technical language and into time, and they place these things somewhere between 500 and 700 million years after the beginning. The universe, at that point, was about 4% of its current age. If you compressed the whole history of the cosmos into a single year, with the Big Bang at midnight on the 1st of January, these objects would be showing up in the second week of January. Everything else, every star you can name, every planet, every galaxy in your mental image of the night sky, is still 11.5 months away. Now here is what made the paper land the way it did. When the team fitted the light from these 6 objects using the standard tools, treating them as galaxies and asking how many stars would be needed to produce that much light, the numbers came out enormous. Each of the 6 carried more than 10 billion solar masses of stars, and one of them came out near 100 billion. 100 billion solar masses of stars is roughly the Milky Way. Our galaxy, the one that took 13 billion years to build, apparently already finished and sitting there when the universe was 600 million years old. That is the sentence that broke containment. It is worth sitting with why that particular claim is so hard to swallow, because it is not merely surprising. Our galaxy contains somewhere in the region of 100 to 400 billion stars, and it did not arrive that way. It was assembled. The Milky Way we live in is a composite object, built up over more than 13 billion years out of smaller pieces that fell into each other, one merger at a time, with each collision stirring gas, triggering new star formation, and leaving behind streams of stars that astronomers can still trace through the halo today. There are the remains of at least a dozen swallowed galaxies wound through the structure around us. That is what 100 billion solar masses of stars normally costs, essentially the entire age of the universe spent building. So a Milky Way at 600 million years is not a fast version of the same process. It is a different process, or no process at all. Within about a week the story had spread everywhere, and it had lost its shape on the way. Webb has found galaxies that should not exist. Webb has broken cosmology. Webb has disproved the standard model. The word candidate, which is sitting right there in the paper's title, does not appear in almost any of the coverage. Neither does the phrase from the abstract that says, in plain language, that these results would need to be verified with spectroscopy, meaning the team themselves flagged that they had measured colours, not spectra, and that colours can mislead you. But I want to be fair to the alarm because the alarm was not silly. There was a genuine problem here, and serious people were genuinely worried about it. The standard model of cosmology is specific. It is built on cold dark matter, on dark energy, and on a set of initial conditions in the very early universe, and from those ingredients it makes quantitative predictions about how fast structure can assemble. Tiny density fluctuations in the early universe grow under gravity. Matter falls together, halos of dark matter form, gas falls into them, stars condense out of the gas. All of that takes time, and the model tells you how much time. One extremely massive galaxy showing up early can be absorbed. The universe is a big place and rare things happen. But a whole population of them, appearing in the first small patch of sky anyone looked at, is a different kind of problem, because if you find several in a tiny field, then there must be an enormous number of them across the whole sky. And there is a harder version of the objection that does not depend on how quickly stars form. It is about how much material there is to work with. A dark matter halo of a given mass can only contain so much ordinary matter. The ratio is fixed by cosmology, and it is well measured. If you take one of these early halos and convert every single atom of available gas inside it into stars, with perfect efficiency and no waste at all, you still cannot always reach the stellar masses that were being reported. That argument is much harder to escape than a star formation rate argument, because it does not care how fast anything happens. It is an accounting limit. What almost nobody outside the field noticed is that the counter-argument arrived almost immediately, and it arrived in the same year. Another group posted a paper whose title reads like a direct reply: Confirmation of the standard cosmological model from red massive galaxies approximately 600 million years after the Big Bang. Same objects, same data, opposite headline. That is not a scandal, and it is not two teams contradicting each other out of stubbornness. It is what a live scientific question looks like before it settles. The measurements were not in dispute. What was in dispute was what you are allowed to conclude from them, and that turns out to be a much harder question than measuring anything. There is one more thing about the timing that is easy to miss. Webb released its first full-colour images in July of 2022. The Labe paper came out in February of 2023. The entire impossible galaxies controversy, the headlines, the panic about cosmology, the papers arguing both ways, all of it happened inside the telescope's first 18 months of operation. This was not a slow accumulation of evidence over a decade. It was a machine switching on and immediately handing everybody a problem. So for a stretch of months in 2023, that was the story. The telescope had found something that the framework could not hold. Headlines said the standard model needed rewriting. Some researchers genuinely wondered whether the way we understood matter clumping together in the early universe would have to be rebuilt from the ground up. And here is where the story starts doing something I did not expect the first time I followed it, and it is the reason I wanted to make this video rather than one about a straightforward discovery. Astronomers went and did the arithmetic more carefully, not to defend the standard model, and not to make the anomaly go away. They did it because that is the next step, and the next step happened to lead somewhere nobody had planned to go. Because if you take the light from one of these objects and you insist that all of it is starlight, and you work out how many stars are needed, and then you take that number of stars and try to fit them inside the measured size of the object, something goes badly wrong. And the thing that goes wrong is not a small discrepancy or an awkward tension. It is a contradiction that closes on itself from both sides at once, and it takes the entire explanation down with it. But to see how that happens, you first need to know what else was being found while everyone was arguing about 6 objects in one patch of sky. Because those 6 were not the population, they were the corner of it. Part 3. Everybody started finding them. The Labe paper landed like a stone dropped into still water, and the interesting part was not the splash, it was the ripples. Because the moment those 6 objects were described in print, every other team with time on the telescope went back through their own data looking for the same thing, and they found it. Not occasionally, not in 1 or 2 fields, everywhere they looked. A team led by Jorrit Matthey picked up the trail next, working with 2 surveys that had been designed for completely different purposes. One is called Eiger, and it was built to study the environments around distant quasars. The other is called Fresco, and it was built to survey emission line galaxies. Neither program was looking for compact red objects. Both of them were full of compact red objects. The dots were, in the most literal sense, by catch. They turned up in nets set for something else. What Matthey's team did that mattered was search specifically for broad emission lines, which I will come back to in detail because it becomes one of the central threads of this whole story. What they found was an abundant population of sources sharing 2 defining characteristics. They were red and they were small. And in their 2024 paper in the Astrophysical Journal, they gave the objects a name, little red dots. It is, I think, one of the great understatements in the history of astronomy. Here is a population of objects that will go on to dismantle a set of confident measurements and force the invention of a whole new category of astrophysical body, and the name it carries is the sort of thing you would write on a sticky note. Astronomers have historically been quite good at grandiose naming. Quasar, pulsar, magnetar, blazar. This one got called Little Red Dots, and the name stuck immediately and completely. It is now the standard term in the literature. You will find it in Nature papers, and once the name existed, the census began in earnest. JDs came online, a deep survey run jointly by the teams behind 2 of the telescope's main instruments. ENGDeep went deeper still, in a different patch. Ruby started hunting specifically for unexplained red sources. The acronym stands for Red Unknowns, Bright Infrared Extragalactic Survey, which tells you exactly how the field felt about these things by that point. Primer, Uncover, and Cosmos Webb all added their own catalogues. Cosmos Webb in particular covered a wide field rather than a narrow deep one, which meant it could ask a different question. Not how faint can we go, but how common are these across the sky? The answer was very. By the time the surveys had reported, there were hundreds of little red dots identified, distributed across essentially every deep field the telescope had ever produced. This was not an instrumental artifact. It was not one team's processing pipeline misbehaving. It was not a chance alignment in one unlucky patch of sky. It was a genuine population, and it was numerous. I want to pause on the fact that these things were found by accident, because it says something about how discovery actually works that the tidy version of science never mentions. Nobody proposed to look for little red dots. Nobody could have. You cannot write a telescope proposal to search for a category that does not exist yet. Time on this instrument is fought over ferociously. The oversubscription rate runs to several times more requested hours than there are hours available, and every successful proposal has to argue for a specific, well-motivated target. So every single one of these objects was found by somebody who was looking for something else, in data taken for a different purpose, by a team who then had to stop and ask what the extra thing in their frame was. The most consequential result of the JWST era so far arrived in the margins of other people's work. But the strangest thing about the census was not how many there were. It was where they sat in time. Almost all of them appear in one specific window of cosmic history. They begin showing up around redshift 8 or 9, which is somewhere around 600 million years after the Big Bang. Their numbers climb, they reach a peak around redshift 6 or 7, and then, moving forward in time, they fade out, dropping away sharply below about redshift 4, which corresponds to roughly 1.5 billion years after the beginning. There is a thin tail of them that survives to later times, and one of those stragglers turns out to be the single most important object in this entire story. But the bulk of the population lives and dies inside that window. That shape, a rise, a peak, and a fall, confined to a particular stretch of cosmic time, has a name. Cosmologists call it a population epoch. It describes a situation where particular physical conditions exist for a while, are exploited by some process, and then close as the universe moves on and the conditions stop being available. The textbook example is reionization. In the early universe, after things had cooled enough for atoms to form, space was filled with neutral hydrogen gas, a fog, essentially, that light could not travel far through. Then the first stars and the first bright sources switched on, and their ultraviolet light began stripping electrons off that hydrogen, carving out transparent bubbles. The bubbles grew, merged, and eventually the whole universe went from opaque to clear. That transition happened once, took a few 100 million years, and can never happen again, because there is no neutral fog left to clear. It was an epoch. It opened, and it closed. The little red dots appear to define an epoch of their own, nested inside that broader story of cosmic dawn. Something about the conditions in the first 1.5 billion years made these objects possible and common, and then the universe changed and they stopped being made. That framing is important, and I want to flag it now because it shapes everything that follows. If the dots were scattered evenly through cosmic time, they would probably be some kind of object we already know about, seen at an odd angle or in an unusual state. The fact that they cluster in one era and then stop suggests something else. It suggests that they depend on conditions the universe only had once. Whatever a little red dot is, it is bound up with a particular chapter. The chapter when the first stars ignited, when the first galaxies pulled themselves together, and when the first supermassive black holes somehow appeared at sizes that current physics still struggles to account for. There is also something quietly moving about looking at an epoch that has closed. When you photograph a little red dot, you are photographing a kind of object that the universe does not make anymore. Not one that is rare now, or hard to find now, one that stopped. Whatever set of circumstances allowed these things to exist, some particular combination of gas density and chemistry, and the way matter was arranged when everything was still crowded together, those circumstances expired, and the universe kept going without them. The only reason we can see them at all is that light is slow, and the skies are recording. Point a telescope far enough out, and you're not looking at a distant place. You're looking at a closed chapter, still in progress, because the news has not finished arriving. So the question changed shape. By the middle of 2024, nobody was asking whether the little red dots were real. That was settled. Everybody was asking what they were, and this is the point at which the field started reaching for the boxes, because there is a catalogue. Astronomy has spent 1.5 centuries sorting the sky into categories, and those categories are good. They are the accumulated result of an enormous amount of careful work, and they cover, as far as anyone knew, everything that a bright compact object in the distant universe could reasonably be. 3 explanations were obvious enough that essentially everyone reached for them at the same time. Maybe these are very old galaxies, seen from very far away. Maybe these are feeding supermassive black holes hidden behind dust. Maybe these are unusually tight clusters of stars packed together far more densely than anything nearby. Every one of those was tested against the data, and every one of them failed, not by a little, and not in a way that could be patched. To see how, we need to look at what the measurements actually said, because there are 3 of them, and each one on its own would be strange. Together, they do not describe anything in the catalogue at all. Part 4. 3 measurements and a surplus. A small red point of light should be one of the easiest things in the sky to interpret. It is small because it is far away. It is red because it is old, or because it is behind dust, or because the expansion of the universe has stretched its light. Those are the 3 explanations. They cover essentially everything, and normally that is where the analysis ends. Astronomers have been sorting small red things for a very long time, and they are good at it. The little red dots refused all 3 endings, and they did it through 3 specific measurements, each of which is strange on its own, and which together describe nothing that exists in the catalogue. The first measurement is the shape of the light. When you take light from an object and break it apart by wavelength, the way a prism splits sunlight into a band of colour, you get a spectrum, and the spectrum is where nearly all the information lives. The brightness at each wavelength plotted out across the range gives you a curve, and curves have shapes, and shapes have meanings. Normal galaxies produce smooth curves. Dusty galaxies produce smooth curves that lean red. Ordinary feeding black holes produce smooth curves too, with characteristic bumps in particular places. Everything in the local universe produces something reasonably continuous. The little red dots produce a V. There is a thin trickle of blue light on one side, then an abrupt step, then a flood of red light on the other side, far brighter than the blue. Plot the brightness across wavelength and the pattern traces a clean V shape, with a sharp corner in the middle. Almost nothing in the catalogued universe looks like that. The step itself sits at a specific place, and the place has a name, the Balmer break. Hydrogen atoms absorb light at particular wavelengths depending on which energy level their electron is sitting in, and there is a series of absorptions associated with electrons in the second energy level. Those absorptions crowd closer and closer together as you go up in energy until they merge into a continuous wall at 364.6 nanometers. Light bluer than that gets absorbed heavily. Light redder than that passes. The result is a step in the spectrum. Now here is the crucial thing, and it is the hinge on which this entire story eventually turns, so hold on to it. In ordinary galaxy work, a strong Balmer break means one specific thing. It means the galaxy contains a large population of A-type stars, which are the stars that produce that absorption most strongly, and A-type stars dominate a population that is a few 100 million years old. The break is used routinely and correctly as an age indicator. A big break means an evolved population. That is the standard reading. It works essentially everywhere, and it is the origin of the entire too old, too early story you heard about in 2023. The second measurement is size. These objects are not merely compact for their distance. They are absurdly, almost aggressively small. A typical galaxy in the modern universe spans tens of thousands of light years. Our own Milky Way is around 100,000 light years across. Matthey's sample put the typical little red dot at an effective radius of roughly 150 parsecs, which is somewhere under 500 light years. And the tightest constrained cases, measured using gravitational lensing where a foreground cluster of galaxies bends and magnifies the light of something behind it, come in far smaller than that. The single best-studied object in the population has a formally best-fitting effective radius of about 40 parsecs. That is around 130 light years. It is worth understanding how a measurement like that is even possible, because at these distances the objects are far smaller than the telescope can resolve. The trick is to let the universe lend you a bigger lens. A massive cluster of galaxies sitting between us and a distant source bends the light passing around it in exactly the way general relativity says mass should bend light, and the result is that the background object is both magnified and stretched. Astronomers can model the cluster's mass distribution, work out how much stretching it applied, and effectively undo the distortion, which gives them a sharper view of the background source than the telescope could ever produce on its own. It is a borrowed lens made of dark matter and galaxies, and it is the only reason we have any tight size limits on these objects at all. Let me put that in a shape you can hold. Imagine the Milky Way shrunk down to the size of a football stadium. The whole thing, 100,000 light-years of spiral arms, 400 billion stars, the dust lanes, the halo, all of it, compressed into 100 meters of turf and terracing. On that scale, our sun and everything around it out to the nearest few hundred stars would be smaller than a grain of sand somewhere out toward the touchline. Now walk up into the stands, pick a seat. Any seat, halfway up, nothing special about it. Sit down. The seat is bigger than a little red dot. That is the size comparison, and it is not a rhetorical flourish, it is the arithmetic. And now add the second half of it. That object, smaller than the seat you're sitting in, is putting out roughly as much light as the entire stadium. All of it. Every star in the shrunken galaxy laid out in front of you. All of that light, coming out of a volume you could reach around with your arms. And then add the third piece. Around that seat, hydrogen gas is moving at thousands of kilometers per second. Fast enough to cross the Atlantic Ocean in about a second and a half. Fast enough to go from the Earth to the Moon in under 2 minutes. Circling something you cannot see in a space smaller than the chair you're sitting in. That third piece is the third measurement, and it is the one that put black holes into the story. Astronomers looked at the light coming from hydrogen gas around the dots, and the emission lines were not sharp. They were smeared out across a wide range of wavelengths. That happens when gas is moving toward you and away from you at the same time on opposite sides of the same object. The light from the approaching side is shifted blue, the light from the receding side is shifted red, and what you see is the sum of all of it, broadened out. Measure the width of the smear and you can read off the speed. The speeds came out in the thousands of kilometers per second. In the best study case, the hydrogen alpha line has a width of about 1,500 kilometers per second. Gas does not move that fast on its own. Gas is lazy. To whip a cloud of hydrogen around at those speeds, you need a gravitational anchor of extraordinary strength, and there is essentially one candidate that fits: a black hole and a big one. This is the standard method for weighing a black hole you cannot see directly, used across all of extragalactic astronomy, and it is why supermassive black holes moved to the center of this story, and stayed there for 3 years. Remember that. Line width equals speed, speed equals mass. It is going to matter enormously later, and the masses that came out of that calculation were the part that made everybody uncomfortable. Not because black holes in the early universe are surprising in themselves. We have known about distant quasars for 60 years. It was the proportions. In the nearby universe, there is a very reliable relationship between the mass of a galaxy's central black hole and the mass of the galaxy around it, and the ratio sits at roughly 1 part in 1,000. The black hole at the center of our own galaxy, Sagittarius A star, weighs about 4.3 million suns, and the Milky Way around it weighs several hundred billion. That relationship is one of the more remarkable regularities in astronomy, because it implies that galaxies and their central black holes grow together, regulating each other somehow over billions of years. The little red dots did not obey it. The numbers coming out of the line widths implied black holes carrying somewhere between 1 and 10% of the total mass, 10 to 100 times more than the local relationship allows. Objects that were, in the field's phrase, overmassive. Black holes that had somehow got ahead of their own galaxies, at a point in cosmic history when there had barely been time for either. And then, on top of all 3 measurements, there was an arithmetic problem that had nothing to do with any individual object. Across the surveyed sky, astronomers were finding roughly 10 times more of these things than any extrapolation from the known population of bright early black holes would have predicted. Not 10% more, 10 times. An order of magnitude surplus is a very specific kind of signal. When a measured population exceeds a theoretical prediction by a factor of 10, it almost never means that somebody dropped a decimal point or misjudged a correction factor. Errors of that scale are usually structural. It typically means the model is not slightly miscalibrated. It means the model is missing something, an entire physical regime that nobody had written in, because nobody knew it was there to write. So here is what astronomers were looking at by the middle of 2024, objects far too small for their brightness, light shaped in a way no known galaxy or black hole produces, hydrogen moving at speeds that demand an enormous hidden mass, and 10 times more of them than anything in the existing models allowed. And I want to name something quietly here, because it will matter at the end. Every single one of those statements is an inference, Nobody has ever visited a galaxy. Nobody has flown out and measured one. What we have is light, arriving after 13 billion years, in quantities small enough to count individual photons, and a set of very good rules for turning that light into numbers. The rules are the achievement. The rules are what a century and a half of astronomy actually is. Keep that in mind, because the rules are about to be applied to something they were never built for. Part 5. The theory that ate itself. The simplest answer to a red object in space is that it is old. This is one of the most reliable rules in astronomy, and it is worth appreciating how good a rule it is before we watch it fail. Young stars burn hot and shine blue. As a population of stars ages, the hottest and most massive members die off first, because burning brightly is expensive and they run out of fuel fastest. What is left behind are the cooler, redder, longer-lived stars, and they gradually come to dominate the light. A galaxy's colour is, among other things, a written record of its own history. Read the colour, and you are reading the star formation story back out. So when astronomers first saw compact red sources in the deep fields, the instinct was the natural and correct one. These must be old galaxies. Galaxies packed with cooler, evolved stars that have long since passed through their brightest phase. That is what red means. The trouble was never the colour. The trouble was the clock. The little red dots sit at less than 1 billion years after the Big Bang. If they were already mature galaxies, full of evolved stars weighing as much as the Milky Way, then they had to have been built astonishingly fast, and then, on top of that, had to have already stopped. Because a galaxy that has quenched, that has gone quiet and turned red, must first have finished forming its stars. So old and dead at 600 million years implies furiously forming stars at 300 million years, which does not solve the timing problem. It moves it earlier and makes it worse. The standard cosmological picture does not allow finished Milky Ways that early. There is not enough time for gas to fall in, cool, condense, and form that many stars. And underneath the time problem there is the accounting problem I mentioned earlier, which is much harder to argue with. A dark matter halo of a given mass can only hold so much ordinary matter, and even converting every available atom into stars with perfect efficiency, some of these objects came out too heavy. But none of that is what killed the theory. What killed the theory was density, and the way it happened is the most elegant thing in this whole story. Here is the argument. Take the light coming from one of these dots. Assume, as the theory requires, that every photon of it is starlight. Work out how many stars you need to produce that much light. The number is enormous. In the best studied case, a formally best-fitting stellar mass of something like 30 billion suns. Now take that many stars and try to fit them inside the measured size, 40 parsecs, 130 light-years. The density you get is unlike anything in the catalogued universe. To understand what that means, think about your own neighbourhood. The nearest star to the Sun is Proxima Centauri, and it is 4.2 light-years away. That is not a large gap by cosmic standards, but in human terms it is an emptiness that is difficult to hold in mind. If you shrank the Sun to the size of a grain of sand and put it on a table, Proxima would be another grain of sand about 25 kilometres away, and the space between them would contain essentially nothing. That is what a normal stellar neighbourhood looks like. Stars almost never touch. Collisions between stars are so rare in a galaxy like ours that in the entire history of the Milky Way, in a volume containing hundreds of billions of stars, direct collisions have been vanishingly uncommon events. Now pack an entire galaxy's worth of stars into a region 130 light-years across. At those densities, the analysis in the paper concludes stellar collisions would be happening on something like a monthly basis, and stars are not soft. When two stars run into each other at galactic velocities, the result is not a gentle merging. It is a release of an enormous amount of high-energy radiation, precisely the kind of light that punches through gas and dust and reaches X-ray telescopes from across the observable universe. If the little red dots really were that dense in stars, then the sky should be glowing with the wreckage. We should be seeing X-ray light pouring out of them, flares, bursts, the distinctive signatures of stars tearing each other apart over and over in a permanent slow-motion pile-up. Astronomers looked. They took hundreds of these objects, stacked their X-ray observations together to push sensitivity past what any single object could give, and waited for a signal to emerge from the combined data. The signal stayed silent. I should explain what stacking is. because it is one of the quiet workhorses of modern astronomy, and it makes the silence much more meaningful than it might sound. If you take a single image of a faint object, the signal you want is buried in noise, random fluctuations from the detector, from the sky, from the electronics. But noise is random and signal is not. Add together 100 images of 100 similar objects, and the random noise partially cancels itself out, while the real signal adds up straightforwardly. Mathematically, the noise grows as the square root of the number of images, while the signal grows in direct proportion. So stacking 100 sources buys you roughly a factor of 10 in sensitivity. It is a way of asking a question of a population that no individual member is bright enough to answer, which means a stacked non-detection is a far stronger statement than a single non-detection. It is not, we looked at one and did not see anything. It is, we combined everything we have, pushed the sensitivity as far as the archive allows, and the place where the signal should be is empty. And this is the trap, and it closes from both sides at once. Either the dots are far less dense than they appear, in which case the all-starlight picture cannot possibly explain how bright they are, because you no longer have enough stars, or they really are that dense, in which case they should be screaming in X-rays, and they are not. Neither door stays open. You cannot have it both ways. The team that ran this analysis most carefully went further and closed the remaining escape routes. Maybe the stars are unusual. Maybe the mix of stellar masses in the early universe was different from today, weighted toward the kinds of stars that would produce this light more efficiently. They tested it. Reasonable variations in what astronomers call the initial mass function do not rescue the picture. Maybe there is dust doing something exotic, some unusually steep reddening law that we do not see nearby. They tested that too, with unusually strong and unusually steep attenuation. It does not work either. There is a deeper principle underneath all of this, and it is worth stating because it recurs later in the story from the opposite direction. Any object producing an enormous amount of light from a very small region needs an energy source that is both incredibly powerful and incredibly concentrated. Stars generate energy by nuclear fusion, and fusion has a ceiling. At a certain point, it is called the Eddington limit. The outward pressure of a star's own radiation becomes strong enough to balance the inward pull of its own gravity. Push past that point and the star cannot hold itself together properly. It begins to shed its outer layers, or comes apart entirely. Under the all-stellar explanation, the little red dots would need stars shining so far beyond that ceiling that they could not remain stable long enough to be observed as a population. They would effectively destroy themselves almost as soon as they formed. There is one more strand worth pulling, because it concerns dust, and dust turns out to matter in both directions. If you want to explain a red object by saying it is behind a screen of dust, you have to explain where the dust came from. Dust grains are not primordial. They are manufactured, forged in the outer layers of evolved stars and thrown out in supernova explosions, made of carbon and silicon and the other elements that only exist because a previous generation of stars fused them. So a dusty object at 600 million years requires a whole prior generation of stars that has already lived, died, and enriched its surroundings. That is not impossible, but it is another item on a bill that was already looking expensive. And when astronomers actually measured how much dust is present in these systems, one team at the University of Texas at Austin found roughly 1% of what the dusty starburst models needed. Not a shortfall, an absence. So the first theory did not just fail to fit the data, it collapsed under the weight of its own assumptions, and it did so in a way that is genuinely satisfying to watch, because the contradiction is entirely internal. You do not need any new physics to break it. You just need to take the theory seriously and follow it 2 steps further than it wants to go. Which leaves you with the only other kind of object in astrophysics capable of producing that much light from that smaller volume and sustaining it over long stretches of cosmic time without either exploding or going out. An accreting black hole. And that theory was already waiting. Part 6. The Campfire In The Blanket. A feeding black hole, in the right circumstances, can outshine an entire galaxy on its own. This is one of the most useful facts in astronomy, and it is worth pausing on how strange it is. A black hole emits nothing. That is essentially its definition, a region where gravity has become steep enough that not even light can climb out. And yet the brightest sustained objects in the known universe are powered by black holes. The resolution is that the light does not come from the black hole, it comes from the Q. When matter falls toward a black hole, it does not drop straight in. anything with even a small amount of sideways motion goes into orbit instead, and because there is a lot of material trying to do this at once, it piles up into a flattened, swirling disk. That disk is not calm. The inner parts orbit faster than the outer parts, so adjacent layers of gas grind against each other, and friction turns orbital energy into heat. Enormous amounts of heat. The inner regions of an accretion disk around a supermassive black hole can reach temperatures where the material radiates across nearly the whole spectrum, from radio waves right up through the ultraviolet and into hard X-rays. We have known about these things for over 60 years. Quasars are exactly this, a black hole at the heart of a galaxy, feeding hungrily and blazing so brightly that it drowns out every star in the galaxy around it combined. The first ones discovered were so bright and so far away that nobody could believe the distances at first. So the second instinct was completely reasonable. Maybe the little red dots are just small early galaxies with a feeding black hole at the centre, wrapped in thick clouds of dust that absorb the bluer light and let only the redder light through. The technical term is a dust-obscured active galactic nucleus, and there are plenty of them in the nearby universe. It would explain the redness, it would explain the brightness, it would explain the compactness, and it would explain the fast-moving hydrogen. Think of it as a campfire wrapped in a heavy blanket. The bright flame at the centre is hidden from view, but the heat still leaks through. The blanket itself warms up and starts to glow. Sparks and radiation escape around the edges. If you have the right instruments, you can detect every part of that story. The leaked heat, the warm blanket, the escaping sparks, even though you never see the flame. That is a good picture. It is also a picture that makes very specific, very testable predictions, and every one of them was tested. The first prediction is X-rays. A feeding black hole in the early universe should be a bright X-ray source, and X-rays are the part of this that is hardest to hide. Visible and ultraviolet light get absorbed by dust easily. X-rays carry far more energy per photon, and they punch through almost anything. That is the whole reason X-rays are useful in a hospital. They go through the soft parts. If there is a black hole feeding behind a blanket, the X-rays come through the blanket. NASA's Chandra X-ray Observatory has been watching the sky for more than 2 decades and has built up an enormous archive. Astronomers went to that archive and looked for little red dots, repeatedly, using different samples and different methods. One team stacked 21 high redshift dots together. Nothing came out. Another team, working independently with a different selection, reached comparable conclusions. A third group cross-matched the JWST catalogues against Chandra and described what they found as a large population of sources that are either buried behind an absorbing column so thick that even X-rays struggle, or else are simply, intrinsically, X-ray weak. Only a handful of these objects have ever been detected in X-rays at all. As a population, they are far fainter in X-rays than the dust-shrouded black hole picture requires. Not marginally fainter, not at the edge of the error bars, wrong by a wide margin. There is a way out of this, and it deserves a fair hearing because serious people defend it. The escape route is called Compton thick absorption, and it means burying the black hole behind a column of material so dense that even X-rays cannot get through. Not by being absorbed in the ordinary way, but by scattering off free electrons so many times on the way out that they effectively never leave. The threshold is a column density of something like 1.5 times 10 to the 24th particles per square centimetre along the line of sight, which is a genuinely enormous amount of material stacked between you and the source. Some fraction of local active galaxies are Compton thick, so it is not an invented mechanism, but invoking it here has a cost. To hide the X-rays of every little red dot in the sky, you need essentially every one of them to be wrapped in an extreme absorbing column, seen from every possible angle, with no gaps and no sightlines that happen to look down the axis. In the local universe, obscuration depends on orientation. You see some active galaxies face on and unobscured, others edge on and buried, and the mix tells you about the geometry. A population that is 100% buried, with no exceptions, is not a population that is being hidden by chance. It is a population where the hiding is built into the object. Hold that thought. It turns out to be almost exactly right, for reasons nobody had guessed. The second prediction is warm dust. If a black hole is feeding behind a thick blanket, then the blanket has a job to do. It absorbs the radiation coming from inside, and absorbing radiation means gaining energy, and gaining energy means heating up. Warm dust glows, and it glows in the mid-infrared. This is not a subtle prediction, it is unavoidable. You cannot have a dust screen absorbing an enormous luminosity without that dust getting hot and re-radiating. The telescope has an instrument built precisely for this. MIRI, the mid-infrared instrument, works at wavelengths where warm dust is brightest, and it is the coldest and most demanding part of the observatory. It needs its own dedicated cryocooler to run at around 7 Kelvin, and mid-infrared observing time is among the most fiercely competed for on the whole telescope. Astronomers spent that time pointing MIRI at the dots and looking for the glow. Where the signal should have been bright, it was flat. The warm dust is not there in anything like the quantities the model needs. The third prediction is radio. Radio waves are the cleanest test of all, because radio does not care about dust. At those wavelengths, dust grains are so much smaller than the wave that the light passes through as if the dust were not present. If a dust-cloaked black hole is sitting at the centre of one of these objects, the radio emission from its core should reach us essentially undimmed. Astronomers stacked radio observations of hundreds of little red dots, including from the wide Cosmos Web survey. The paper that came out of that work is published in Astronomy and Astrophysics, and it has a title that tells you the result before you read a word of it. Deep silence. Nothing came back. I find that title quietly remarkable. Scientific paper titles are usually flat by convention. A description of the method, a statement of the result, no adjectives. Somebody chose those two words deliberately, and they chose them because after stacking hundreds of objects across one of the widest deep surveys ever taken, at wavelengths where dust is irrelevant and hiding is essentially impossible, there was nothing there. Not a faint detection, not a marginal excess. Silence, at depth. So by the end of 2024, the situation had a shape that is genuinely difficult to sit with. The hydrogen gas inside these objects was moving as though there were a powerful black hole at the centre, churning matter around at thousands of kilometres per second. That measurement was solid. It had been repeated across many objects by many groups, and it demanded an enormous concentrated mass. And every other calling card of a feeding black hole was missing. The X-rays were missing. The warm dust was missing. The radio was missing. 2 natural categories, both eliminated not by argument, but by observation, by people who mostly wanted them to work. I think that last part is worth saying out loud, because the version of science that reaches most people is a version where somebody has a brilliant idea and is proved right. What actually happened here is that a large number of extremely capable researchers proposed the 2 most sensible explanations available, and then spent 2 years methodically demonstrating that their own explanations were wrong. Nobody was forced into it. There was no rival camp applying pressure. The X-ray stacking, the mid-infrared searches, the radio work, all of it was done by people inside the field, testing their own preferred answer, publishing the null results, and moving on. That is an unglamorous kind of integrity, and it is the only reason the rest of this story exists. The dots were not impossibly mature galaxies. They were not dust-cloaked black holes either. Whatever they were not in the catalogue, and the catalogue was supposed to be complete. But there was one more test, one signature that neither dust nor distance nor geometry can suppress, one question that a feeding black hole cannot decline to answer, and when they finally asked it, the answer was worse than silence. Part 7. They do not twinkle. There is one test that a feeding black hole cannot refuse to take. Dust can hide X-rays. Geometry can hide almost anything, if you are willing to make enough assumptions about orientation. Distance can hide detail. But nothing about dust, distance, or angle can stop an object from changing. A feeding black hole flickers. This is not a subtle effect, and it is not controversial. The accretion disk around a black hole is a turbulent, unstable structure. Clumps of gas fall in unevenly. Hot spots form and shear apart. The inner edge of the disk wobbles. The result is that the total brightness of the object goes up and down, on timescales that range from hours to decades depending on the mass of the black hole and the wavelength you're watching in. Astronomers have used this for half a century as the definitive remote test. It is the cleanest identification method there is. Find a suspiciously bright compact source, watch it, come back in a few months and watch it again. If it has changed, you are almost certainly looking at an active galactic nucleus, because there is essentially nothing else that behaves that way. And crucially, stellar populations do not vary. Individual stars do, Plenty of stars pulse or flare or eclipse each other. But average millions of them together and all of that individual variation cancels out into something that is, for observational purposes, absolutely constant. A galaxy's starlight does not change from year to year. It cannot. There are too many independent contributors, so variability is the one unambiguous discriminator. Black hole, yes. Stars, no. It is the closest thing this field has to a clean binary question. They asked it, and the little red dots did not vary. The work has been done several times now by different groups at increasing scale, and the answer keeps coming back the same. An early study analysed roughly 300 multi-epoch sources, objects that had been imaged more than once at different times, and found only tentative variability in a small minority. A larger effort compiled 806 little red dots across 5 separate deep fields, of which 314 had multiple detections, and found that their distribution of measured changes was statistically indistinguishable from what you would expect from a population that does not change at all. Then, in April of 2026, a dedicated program published its results, and the paper has one of the best titles I've encountered in astrophysics. It is called How I Wonder What You Are, JWST's Little Red Dots Do Not Twinkle. That program was the first joint spectroscopic and photometric time domain study of these objects, meaning they did not just measure brightness at 2 moments, they took spectra and photometry together, repeatedly, over time. They monitored a complete sample of 18 dots selected by hydrogen alpha brightness at redshifts between 3.9 and 6.8, with a rest frame baseline of roughly 140 to 220 days. That last number matters. Because of redshift, time itself runs slow in these images, so covering a few months in the object's own frame means watching for years in hours. They do not twinkle. Out of 18 objects monitored properly with spectra and images taken together over a genuinely useful baseline, the population sat still. And that null result carries more weight than any of the earlier ones, because this study was designed for the question rather than assembled out of leftovers. They sit at their brightness, steady, unwavering, in a way that no ordinary feeding black hole does or can. Whatever surface we are seeing is smoothed, either averaged over an emitting area large enough to wash out any internal fluctuation, or physically disconnected from whatever is happening at the centre. It is worth appreciating how much work goes into establishing a negative like this. To say that an object does not vary, you need at minimum 2 good observations separated in time, calibrated well enough that you can be confident any difference between them is real and not an artifact of the instrument, the pointing, the detector temperature, or the data reduction. Telescope time is expensive and repeat observations of the same field are, from a scheduling perspective, a hard sell. You're asking for time to photograph something that has already been photographed. Much of this work was done by mining archives for fields that happened to have been revisited for other reasons, and stitching those accidental repeats into a time series nobody had planned. And there is a second layer of difficulty, which is that when astronomers report no variability, they are not reporting nothing. They are reporting an upper limit, a statement that if the brightness changed at all, it changed by less than some measurable amount. That limit is a real number, and it has to be defended. The claim is not we did not notice anything. The claim is we would have seen a change of this size and there was not one. Let us step back for a moment and put the pieces together, because we have accumulated a lot of them, and the shape of the problem is not obvious until you set them side by side. Astronomy has 4 fundamentally different ways to interrogate a distant bright object. You can look at it in X-rays, which tells you about the hottest and most energetic processes. You can look at it in the infrared, which tells you about warm material and reprocessed light. You can look at it in radio, which passes through obscuration and tells you about the core and any jets. And you can look at it over time, which tells you whether anything is actually happening. The little red dots return nothing on all 4. Meanwhile, the one measurement that does come back loud and clear, the width of the hydrogen lines, insists that there is an enormous concentrated mass in there, with gas whipping around it at thousands of kilometers per second. Gravity says black hole, every observable says no black hole, and the object is too small and too bright for stars. This is the moment I want to sit with, because it is genuinely unusual, and I do not think the popular coverage ever captured it. The problem is not that astronomers could not decide between 2 answers. The problem is that all the answers had been eliminated, and the questions themselves had stopped working. Each of those 4 probes is a language, a way of asking a distant object what it is made of and what it is doing. And here was a population of hundreds of objects sitting in almost every image the most powerful telescope ever built had produced, fluent in none of them. We had the object. We had excellent data. We had 4 independent lines of inquiry, every one of them refined over decades against thousands of known sources, and the thing in the frame would not answer to any of it. There is a particular kind of unease that comes with that. It is not the unease of not knowing something. Astronomy is mostly not knowing things, and that is fine. That is the job. It is the unease of realizing that your instruments are all working perfectly, and the answer they are all returning is that this should not be here. And there is something almost tender in the fact that the paper which stated it most clearly borrowed its title from a nursery rhyme. Twinkle, twinkle, little star, how I wonder what you are. The rhyme is about a child looking up at a point of light and having no idea what it is. 200 years later, with an $8 billion observatory parked at a gravitational balance point 1.5 million kilometers from Earth, somebody wrote that line into the title of a research paper, and it was not a joke, it was accurate. They looked at points of light. They watched to see if they twinkled, they did not, and nobody knew what they were. So the field did the only thing left to do. It stopped trying to fit the objects into the catalogue, and in March of 2025, 3 separate groups of people, on 3 different continents, who had not spoken to each other about any of this, arrived at the same conclusion within the same 60 seconds. Part 8. 1800 Hours. It is Thursday the 20th of March 2025. Every working day, at 1800 hours, Coordinated Universal Time, the Archive preprint server publishes its new submissions. This is the daily heartbeat of physics and astronomy. Papers go up before they are peer-reviewed, before they are typeset, before any journal has touched them, and the entire field reads the new listings the way other people read a morning paper. The 1800 slot is a fixed institutional fact. Everyone knows it. Everyone plans around it. In Copenhagen it is 7 in the evening, and it is still light outside because the equinox was the day before. In Heidelberg it is also 7. In Cambridge, Massachusetts, it is 2 in the afternoon. 3 groups who have not spoken to each other about any of this hit submit into the same minute. Picture the listings page refreshing. The new astrophysics submissions come up in a long column, each with an identifier assigned in order of arrival. And there, sitting almost consecutively, are 3 entries: 2503 16595. Little red dots as young supermassive black holes in dense ionized cocoons. Led author Vadim Rusakov at the Cosmic Dawn Center in Copenhagen, working with Darach Watson. 2503 16596. A black hole star reveals the remarkable gas-enshrouded hearts of the little red dots. Led author Rohan Naidu at the Massachusetts Institute of Technology, with a collaboration of more than 50 people, including Jorit Mathi, Harley Katz, Pascal Ush, Jenny Green, Priyamvada Natarajan, and Marta Voluntari. 2503 16600. A remarkable ruby. Absorption in dense gas, rather than evolved stars, drives the extreme Balmer break of a little red dot. Lead author Anna de Graaf at the Max Planck Institute for Astronomy in Heidelberg, with Hans-Walter Rix, and among the co-authors, Ivo Labbe, the same researcher whose Nature paper 2 years earlier had started the entire episode. 3 teams, 3 institutions, 3 continents, 3 completely different objects at completely different distances, analysed with different methods, and the same answer. It is worth being precise about why simultaneous convergence matters, because it is easy to hear it as a coincidence rather than as evidence. When 3 groups working independently on different data reach the same conclusion at the same time, that is not luck and it is not fashion. It means the data had become good enough that the answer was, in a sense, sitting in it, waiting for anyone who looked carefully enough to find the same thing. In fields where results are contested for decades, you usually see the opposite. One group proposes something, everyone else spends years arguing, and consensus arrives slowly or not at all. Independent simultaneous convergence is the signature of a conclusion that the evidence is forcing rather than one that a personality is pushing. It also removes a whole category of doubt. If one team had proposed this alone, the first question anyone would ask is whether the model was tuned to that team's particular object, or their particular pipeline, or their particular assumptions. 3 teams, 3 objects, 3 pipelines, 1 answer. That question does not really get off the ground. There is a detail in the NIDU paper that I keep coming back to. Every RCIV submission has a comments field, where authors leave practical notes, page counts, journal status, that sort of thing. Flat, administrative text. And in the middle of NIDU's comments field is this line, C. de Graaf et al., in today's archive posting for a black hole star at redshift 3.5. They found out about each other on the way to the door. Somebody, in the last hours before the deadline, discovered that another group was about to publish the same idea about a different object, and rather than racing or hedging or quietly not mentioning it, added a sentence pointing readers at the competition. That is what the field looks like when it is working. And there is one more piece of institutional detail here that I think is the single best thing in this entire story. The spectra behind the NIDU paper came from a JWST observing program, and every program has an official title, submitted with the proposal, long before anybody knows what the data will show. This one is program number 5224, and its title is Mirage or Miracle. Somebody wrote that on a telescope proposal, before the observations existed, before there was a black hole star model, before the 3 papers, before anyone had the faintest idea what these objects were. They looked at the little red dots, understood that the field was staring at something that either was not what it appeared to be, or was something genuinely unprecedented, and put both possibilities in the title, Mirage or Miracle. Hold on to that. It comes back. Telescope proposals are not usually written that way. They are competitive documents, fought over by review panels, and the convention is to sound as though you already know roughly what you will find and merely need the photons to confirm it. Writing a title that openly admits you might be chasing an illusion is not the standard move. Somebody did it anyway, and in retrospect it reads less like hedging and more like the single most honest sentence anybody attached to this whole subject. I like imagining the moment on the other side of that sentence. Somewhere in a building in Heidelberg, somebody opens the new listings the next morning with their coffee and sees their own idea described in a stranger's abstract, filed 60 seconds after theirs, about a completely different object. Whatever you feel in that moment, and I suspect it is complicated, the thing you are also feeling is relief. Because a strange idea proposed alone is a risk. A strange idea proposed simultaneously by 2 other groups who did not know you existed is not a risk anymore. It is a result. So what did all 3 groups propose? Not a new kind of galaxy. Something considerably stranger than that. They proposed a kind of object that had never been catalogued at all. Here is the picture. Take a black hole, pulling matter inward at an extreme rate, the way any feeding black hole does. Now bury it. Completely. Inside an enormous envelope of dense, hot, turbulent hydrogen gas. And I want to be clear about what kind of envelope this is, because the word can suggest something thin and wispy. It is not a halo. It is not a shell of drifting material. It is opaque, and it is enormous. Far larger than our entire solar system, a body of gas so thick that light cannot travel through it in a straight line. The black hole at the core powers the whole structure. Everything you see is ultimately paid for by matter falling into it. But you cannot see the black hole, and you cannot see the accretion disk, and you cannot see any of the machinery. What reaches your telescope is the outer surface of the gas envelope glowing red from the heat of what is happening far below. Think of a hot coal buried in fog. The coal is the energy source. The fog is what you actually see, and from a distance the whole arrangement looks like one steady glowing object, with a temperature and a size and a colour, and you would never guess there was a black hole anywhere in it. NIDU's team modelled it explicitly as a dust-free atmosphere wrapped around a supermassive black hole, with the sharp step in the spectrum and the absorption features produced by dense, turbulent gas rather than by any population of stars. De Graaf's team, working on an entirely different object at a completely different distance, arrived at the same architecture from the other end. The NIDU team's object sits 660 million years after the Big Bang, which puts it deep in the era we have been talking about. Its spectrum has one of the largest hydrogen Balmer breaks recorded at any distance, broad hydrogen beta emission with multiple peaks in it, which is itself a clue, because a simple rotating disk gives you a smooth 2-shouldered profile, not a structured one, and hydrogen absorption showing up in several different transitions at once. And the team put the raw spectra online in a public archive alongside the paper, so that anyone who wanted to disagree with the model could do it with the actual data rather than with the plots. They called it a black hole star, not a black hole in a galaxy, not a black hole behind dust, a black hole that has, for a while, put on the appearance of a star, because the surface it presents to the universe is the outer skin of a hydrostatic ball of hot hydrogen, exactly the way a star's surface is. The difference is only what is underneath. In a star, the energy comes from nuclear fusion in the core. In one of these, the energy comes from something falling in and never coming out. And once you have that picture, every one of the missing signals starts to make sense at the same time. Part 9. The cliff. Every field has objects that do more work than the rest. Not the most beautiful ones, and often not the most extreme ones, just the ones where the physics happens to be written large enough to read. In this story, that object is called the cliff. It came out of rubies, and the name of that survey tells you something about the mood in the field by the time it was proposed. Rubies stands for Red Unknowns, Bright Infrared Extragalactic Survey. Somebody wrote a successful telescope proposal whose central noun was unknowns, not candidate early galaxies, not high redshift active nuclei. Unknowns. Among the sources rubies turned up in a patch of sky called the Ultra Deep Survey Field was an object catalogued as Rubies UDS 154183, which is not a name anybody was going to use twice. It got nicknamed the Cliff, for the shape of the step in its spectrum. Because if the ordinary little red dot produces a V, this one produces something closer to a wall. It sits at redshift 3.55. That places its light around 12 billion years in transit, which makes it one of the later members of the population, one of the stragglers in the thinning tail rather than a first billion years object. That matters, and I want to flag it honestly, because it means the cliff is not itself an example of something impossibly early. What it is instead is the clearest example of the physics, close enough that we can get an exceptionally good spectrum of it. There is a general principle at work in choosing an object like this, and it applies well beyond astronomy. When a phenomenon is confusing across a whole population, the most useful thing you can find is not the average member. It is the extreme one, the case where whatever is going on is turned up so high that it separates cleanly from everything else. Medicine works this way too. Rare severe cases often reveal a mechanism that mild cases hide. The cliff is that case for the little red dots. It is not typical. It is legible, and the spectrum is remarkable. The Balmer break is the sharpest ever measured in any high redshift source, not slightly sharper than the previous record, more than twice as strong as the next strongest example anybody has ever recorded. That is the kind of margin that stops being a data point and starts being a case study. Its broad hydrogen alpha line has a width of about 1,500 kilometers per second. It shows helium emission, and it shows essentially no significant metal lines at all, meaning almost nothing heavier than hydrogen and helium is announcing itself in the spectrum, which is a real constraint on what kind of environment this is. But the feature that mattered most is the one that is easiest to skip past. The cliff shows hydrogen in absorption, not just emission, absorption. That distinction is worth explaining because it is the fingerprint that gives the game away. Emission lines happen when hot gas radiates at characteristic wavelengths. You see them as bright spikes. Absorption lines happen when cooler, denser gas sits in front of a hotter, continuous light source and removes particular wavelengths on the way through. You see them as dark notches. To get absorption, you need a specific geometry, a hot bright source behind and a cooler, denser layer in front, both belonging to the same object. That is precisely the geometry a stellar atmosphere provides. It is why the sun's spectrum is full of dark absorption lines. The hot interior radiates, and the cooler outer layers absorb on the way out. Seeing hydrogen absorption in a distant compact source is therefore a very strong hint that the object has something like an atmosphere, a surface with a layer of cooler gas above a hotter source. The absence of metal lines deserves a moment too because it is doing quiet work in the argument. Everything heavier than helium in the universe was manufactured inside stars and scattered by their deaths. Astronomers call all of it, somewhat cavalierly, metals. Carbon, oxygen, nitrogen, iron, the lot. The amount of it present in an object is therefore a rough clock, and also a rough census of how many generations of stars have lived and died in that neighbourhood. When a spectrum shows strong hydrogen features, and essentially nothing else, it is telling you that whatever this material is, it has not been through much processing. It is close to the composition the universe started with. That is awkward for a mature galaxy reading, which wants a long history of star formation and it is comfortable for a picture involving pristine gas falling in from outside without having spent time inside stars first. So the team led by Anna de Graaf took this one object and ran every available interpretation against it systematically and published the results. Massive evolved stellar populations eliminated, and they did not eliminate it lazily. They tested it against unusually steep dust attenuation laws and against reasonable variations in the initial mass function, the distribution of stellar masses a population is born with, which is one of the more commonly adjusted knobs when a stellar model does not fit. Neither rescued it, and the formally best-fitting stellar solution, the one you get if you force the model to work, gives you a stellar mass of around 30 billion suns inside an effective radius of 40 parsecs, which is the density that produces near-monthly stellar collisions and the X-rays that are not there. Dust-reddened active galactic nucleus, disfavored. And here the team found something specific and important. When they fitted the spectrum from the ultraviolet all the way through to the near-infrared, the data preferred a continuum that is intrinsically redder over one that is being reddened by dust. That is a subtle distinction, and it is worth slowing down for, because it is the difference between two completely different objects. Dust reddening means the source produces ordinary light, and something in front of it is filtering out the blue. The light is red because of what happened to it in transit. Intrinsic redness means the source is producing red light in the first place, because it is a surface at a particular temperature, radiating the way any warm surface radiates. The cliff's light is red at source, which means the redness in these objects is not a screen. It is not a veil over something else. It is the object. The colour is telling you the temperature of a physical surface, and there is a surface there to have a temperature. What survived the elimination was a single picture, a powerful ionizing source embedded in dense absorbing gas. The paper's own conclusion is, I think, the cleanest sentence written about any of this in 4 years. The cliff, they wrote, is the clearest evidence to date that at least some of these objects are not ultra-dense massive galaxies at all, and are instead powered by a central source buried in dense gas. Read that again with the thumbnail of this video in mind. Not ultra-dense massive galaxies, not galaxies. I want to give you a sense of what that conclusion cost because papers compress it out. The cliff was observed with 3 separate instruments: the near-infrared spectrograph, the near-infrared camera, and the mid-infrared instrument, drawing on 2 different observing programs. The preprint went up in March of 2025, went through a revision cycle that ran to July, and appeared in Astronomy and Astrophysics later that year with a 28-person author list. 19 pages of main text and 9 figures to establish what a single smudge of red light is not. That is the ratio, and it is worth internalizing when you hear a confident sentence about a distant object. Behind every such sentence there is usually a document like this, and behind that there are years of telescope time and a couple of dozen careers. And note the care in the phrasing, at least some, not all, not the whole population. One object tested exhaustively, giving one answer, with the honest scope of that answer stated plainly. That is what a load-bearing result looks like, and it is why the cliff is now the reference point everybody argues against. But the model that survived is genuinely strange, and I have been describing it in metaphors: a coal in a fog, a black hole wearing a star. That is fine as a picture, but it is not physics, and the obvious question is how any of that could actually work. How do you hide an X-ray source? How do you stop something that violent from flickering? There is a real mechanism, and it is happening right now inside the sun. Part 10. A black hole. Wearing a star. Let us go inside one. Imagine you are approaching a black hole star from a long way out, and you're somehow able to survive the trip, and you have all the time in the world. From a distance it looks like nothing much. A dull red glow, steady, unchanging, the size of something considerably larger than our entire solar system. If you had instruments, and you measured its surface, you would get a temperature and a radius, and you would write down star and move on. Now go closer, cross the surface. The gas thickens around you almost immediately, and the first thing you notice is that light has stopped behaving normally. Out here in ordinary space, light travels in straight lines and gets where it is going. In here, it does not. Every photon is absorbed by an atom within a very short distance, held briefly, and then re-emitted in some random direction, then absorbed again, then re-emitted again. Light is not travelling through this material, it is stumbling through it, taking a random walk, making almost no progress in any particular direction. Go deeper. The gas is denser now and it is moving, falling inward and falling fast. And here is where something genuinely strange happens. The gas is falling inward faster than the light can climb outward. Radiation produced deep inside is not merely delayed on its way out. It is being carried backwards, dragged inward with the matter that created it. Deeper still, it gets hotter, and the light being produced here is not red at all. It is ultraviolet, and it is X-rays, the hard, high-energy radiation that a feeding black hole always makes. It is being made right now, in enormous quantities, and it will never leave. Every one of those X-ray photons will be absorbed and re-emitted so many times on its way out, losing a little energy at each step that by the time it reaches the surface it is no longer an X-ray at all. It has been ground down. It emerges as the dull red glow you started at, and then, at the centre, there it is. A black hole, feeding. That is the whole object. You walked from a calm red light, through a fog that eats radiation, to a black hole, and back. And from the outside, all of that looks like a single steady star. The mechanism has a name. It is called photon trapping, and it is real, well-understood physics. The condition for it is a comparison of two timescales. Light diffusing out of a dense medium takes a certain amount of time, not because light is slow, but because the random walk is enormously longer than the straight path. Meanwhile, the gas is falling in, and that takes a certain amount of time too. If the gas falls in faster than the light diffuses out, the light is trapped and advected inward with the flow, and this is not exotic. Something structurally similar is happening inside the Sun right now. Energy is generated in the Sun's core by nuclear fusion, and it is generated as high-energy gamma radiation. That radiation does not travel out to the surface and leave. It cannot. The interior of the Sun is dense enough that a photon travels only a tiny distance before being absorbed and re-emitted in a random direction. It random walks, and the time it takes to make that journey from core to surface is estimated at something like 100,000 years. The exact figure depends on the model, and the estimates range over more than an order of magnitude. But it is unambiguously very long. It also arrives changed. What went in as gamma radiation comes out as visible light, degraded step by the countless interactions along the way. So the sunlight falling on your face on a summer afternoon left the Sun's surface 8 minutes ago. But the energy in it was made in the core before our species existed, and it has been stumbling toward the light ever since. A black hole star is that process, applied to a black hole at a scale nothing in the local universe matches, and once you have it, every one of the missing signals resolves. All of them, at once. The missing X-rays make sense, because the X-rays are there, they are just being eaten on the way out. The object is not X-ray quiet because there is no black hole. It is X-ray quiet because the black hole is wearing something. The missing warm dust makes sense because there is barely any dust involved. The redness is not a dust filter over ordinary light. The redness is the temperature of a hydrogen surface. That is exactly what de Graaff's team found in the Cliffs spectrum. Intrinsically red, not reddened. The missing radio makes sense for the same structural reason, and the missing flicker, the hardest fact in the entire dataset, the one that neither dust nor geometry could explain, makes sense too. The envelope is so large and so optically thick that it smooths out everything happening inside it. A campfire behind a thin curtain flickers because the curtain lets the variation through. A campfire behind a wall of fog does not, because the fog averages the light over an enormous emitting area and over the long diffusion time. Whatever the black hole is doing, second to second, is being blurred into a constant by the sheer thickness of what surrounds it. One picture, 4 separate anomalies. That is what a good model looks like. It is worth being explicit about why that matters, because it is easy to be impressed by an explanation that fits and not notice whether it is actually doing any work. A bad model explains one thing and needs a new adjustment for every additional observation, a bit of extra dust here, an unusual viewing angle there, a special assumption for the third measurement. Each patch is individually defensible, and the whole becomes unfalsifiable. A good model is one where a single structural change accounts for several unrelated observations at once, without further tuning. The black hole star does that. You add one thing, an opaque envelope, and the X-rays, the dust, the radio, and the variability all resolve as consequences rather than as separate repairs. and it also predicts something the earlier models did not. If the redness is a surface temperature rather than a dust filter, then the spectrum should look intrinsically red rather than reddened, a difference that is subtle but measurable, and one that had not been specifically tested before anyone had a reason to look for it. There is one more thing the model requires that I have been careful not to skip past, and I want to name it now because it becomes a genuine point of contention. For photon trapping to work at all, the black hole has to be swallowing material extremely fast, at or beyond what is called the Eddington rate, the point where radiation pressure would normally push incoming gas away and throttle the whole process. Super Eddington accretion is theoretically possible precisely because trapped photons cannot push on anything if they cannot escape, so the process partly enables itself. But it is an extreme requirement, and not everyone accepts it. There is a published analysis, using Chandra data, arguing that the X-ray constraints rule out super Eddington accretion models for these objects. That tension has not gone away, and I would be misrepresenting the field if I smoothed over it. And it has an ancestor, which I find genuinely satisfying. In 2008, Mitchell Beagelman and colleagues proposed a theoretical object they called a quasi-star, a black hole growing inside a massive hydrostatic gas envelope, radiating at the envelope's photospheric temperature. It was a piece of pure theory. There was no observational counterpart. It sat in the literature for 17 years as an interesting idea about how the first supermassive black holes might have grown fast enough, occasionally sighted, never confirmed, and then a telescope that had not been built yet took a photograph of a patch of sky, and a decade and a half later somebody realized that the strange red specks in it might be the thing Beagelman had described. Which brings us to what these objects might actually be, in the larger story. If the model holds, the little red dots are not a type of object. They are a phase, a stage in the life of a black hole, the period when it is young, growing violently fast and still buried inside the material it is feeding on. A supermassive black hole's infancy, before it breaks out of its own cocoon and becomes a quasar blazing openly into the universe. A chrysalis, essentially. The buried, opaque, transitional form between a seed and the thing it becomes. And there is now a candidate observation for the moment the cocoon opens. A preprint late in 2025 reported the discovery of two little red dots apparently caught in transition into quasars, the intermediate state, halfway between hidden and revealed. If that is right, then the black hole at the centre of the galaxy you live in spent its infancy looking exactly like this, and there is no photograph of it anywhere, because it happened before anything existed that could have taken one. That is a beautiful picture, and for most of 2025 it looked like the answer. Then one of the three papers went through peer review, and something in it came out the other side that changed what all of this means. Part 11. The fog was the measurement. Vadim Rusakov's paper, the first of the three that went up in that same minute in March 2025, took the longest to arrive in print. It went through 4 versions. It was accepted by Nature. The final version was posted on the 2nd of February, 2026, and it appeared in the journal in volume 649, pages 574 to 579, 47 pages of text, 24 figures, 3 tables. Buried in it is a result that quietly dismantles the most repeated number in this entire field. And I mean quietly. There was no announcement. There was no press cycle to match the one in 2023. It went into the literature the way most important things do, which is without fanfare, in the middle of a long technical paper that most people will only ever read the abstract of. Here is the argument, and I want to build it carefully, because it is the point of this video. Everyone had been reading the broad hydrogen lines as Doppler broadening. That is the standard interpretation, and it is almost always correct. Gas orbits a central mass. The material on the near side of the orbit is coming toward you, and its light is shifted blue. The material on the far side is going away, and its light is shifted red. What you observe is the sum of all of it. So a line that would be narrow if the gas was still comes out smeared across a range of wavelengths. Measure the width of the smear, and you have the orbital velocity. Take the orbital velocity, apply the same physics that lets you weigh the Sun from the Earth's orbit, and you have the mass of whatever is at the centre. This method is not obscure, and it is not a shortcut. It is the standard technique for weighing a black hole you cannot resolve. It is how a very large fraction of the black hole masses in the astronomical literature were obtained. It works. Russakov's team went to the highest quality JWST spectra available for these objects and found that in most of them, the lines are not Doppler broadened at all. They are broadened by electron scattering. Here is what that means. In a sufficiently dense ionized gas, there are free electrons everywhere, not bound into atoms, just loose. A photon traveling out through that gas will bounce off those electrons on its way, repeatedly, and every time it scatters, its wavelength shifts a tiny amount, because the electron it hit was itself moving. Do that once and the effect is negligible. Do it thousands of times and something significant happens. A line that started out narrow comes out of the cloud broad, smeared, spread across a range of wavelengths, and it looks exactly like Doppler broadening. That is the whole problem in a sentence. Two completely different physical processes produce the same observable signature. One of them means gas is orbiting a massive object at enormous speed. The other means light is bouncing around in a fog on its way out. The line looks fast. Nothing is going that fast. Russakov's team could tell the difference because electron scattering leaves a fingerprint. It broadens the wings of a line while leaving a narrow intrinsic core sitting in the middle, the photons that happen to escape without scattering much. Doppler broadening does not do that. It moves the whole line. Once you have spectra good enough to see the shape of the profile rather than just its width, the two become distinguishable. The data required very high electron column densities and emitting regions only light days across. A light day is around 26 billion kilometers, roughly 6 times the distance from the Sun out to Neptune. So the region producing these lines is comparable in scale to a large planetary system, sitting inside an envelope tens of thousands of times bigger, and the team is clear that the black hole is real. Those densities, combined with those luminosities, cannot be produced by anything except accretion onto a supermassive black hole. That part of the picture survives, but the narrow intrinsic cores, the part of the line that reflects actual orbital motion rather than scattering, imply black hole masses between 100,000 and 10 million solar masses, 2 orders of magnitude lower than previously estimated. These are, in the author's own words, the lowest mass black holes known at high redshift. Let me say what that means without the technical language. For 3 years, the field's central anomaly was that the early universe appeared to contain black holes that were far too massive for their surroundings and far too massive for the time available. Overmassive black holes that had somehow got ahead of their own galaxies. It was one of the most cited tensions in extragalactic astronomy. There were review talks about it. There were dedicated conference sessions. There were competing theories about exotic seed formation to explain how they could have grown so fast. They may not have been overmassive. They may have been perfectly ordinary young black holes of a size nobody would blink at sitting inside a fog. And for 3 years, when we measured them, we were measuring the fog. There is a second consequence that follows immediately, and it tidies up one of the other loose ends. Russakov's model has these black holes accreting close to the Eddington limit rather than wildly beyond it, with only mild outflows of neutral gas. That is a much less exotic picture than super Eddington photon-trapped accretion, and it sits far more comfortably with the X-ray constraints, including the Chandra analysis that argued against the super Eddington models. A smaller black hole feeding at a normal rate inside a dense cocoon does not need to break any records. It just needs to be hidden, and the cocoon does that for it. And in this version, the reprocessed light from that cocoon dominates the optical spectrum almost entirely, which means the thing being photographed, when a telescope images a little red dot, is essentially all cocoon and essentially no black hole. Not mostly, almost entirely. Naidu's team had flagged the same danger independently, from the other direction. Their paper states plainly that black hole masses in these objects may be overestimated by orders of magnitude, and gives 2 reasons. The object is effectively dust-free while the standard modelling applies steep dust corrections to it, and the physics generating those complicated line shapes may simply not obey the assumptions built into the standard scaling relations. 2 of the 3 teams, arriving from different directions saying the same thing. The number was wrong. Now sit with the size of that. I want to be careful here, because there is a cheap version of this observation, and I do not want to make it. The cheap version is, scientists were wrong, so why believe anything? That is not what happened, and it is not the lesson. What happened is that a number was published with appropriate caveats, propagated outward through review articles and press releases and videos like this one, gradually shed its caveats along the way and became a thing everybody knew. And then the people closest to it kept testing it until it broke, and publish that too. But the uncomfortable part remains, and I think it is worth naming precisely. Nothing about the wrong number felt different from a right one. It came from a good instrument, through a standard method, in peer-reviewed papers, quoted by careful people. There was no warning sign. Confidence and correctness turn out to be separate properties, and from the inside of the sentence they are indistinguishable. 2 orders of magnitude is not a refinement. It is not a tightened error bar or a small systematic correction. It is the difference between one thing and 100 of that thing. If somebody told you a building was 100 stories tall and it turned out to be a bungalow, that is a factor of 100. That is the scale of the correction. And it was not the result of carelessness. That is the part I want you to hold on to. Nobody cut a corner. The method that produced the wrong number is the correct method, applied correctly, by people who are extremely good at it, using the best data in existence. It is the method that produced most of the black hole masses we are confident about. It works everywhere it has ever been tested. It just does not work on an object that is wearing a fog, because nobody had ever met one before. And electron scattering is not obscure physics either. That is what makes this uncomfortable rather than merely interesting. It is thoroughly understood. It is routinely accounted for in models of stellar atmospheres, where it matters, and in the spectra of supernova, where it matters a great deal. Nobody had to discover it. Every person who fitted a little red dot spectrum knew that electron scattering exists and knew what it does to a line. What nobody had was a reason to think it dominated here, because in every environment astronomers had access to before 2022, it does not. The densities required simply are not found in the objects we can study closely. So the correct default, read the line width as motion, was applied by everyone, because it is the correct default. The error was not in the physics anybody knew. It was in the assumption that this object belonged to the same family as everything else. That is a very particular kind of mistake, and I do not think it has a good name. It is not being wrong about a fact. It is being right about a fact and wrong about which facts apply. Which brings back the title on that telescope proposal, Mirage or Miracle. Somebody wrote that before the data existed, offering the field 2 options, and for 3 years almost everybody took the second one. The objects were treated as a miracle, as a genuine physics-straining, model-breaking population of impossible monsters in the early universe. And the answer, or at least the leading answer now, is closer to the first. Not a fake, not an error, a mirage in the precise optical sense, a real object, seen through a medium that bends what you're looking at into something else. The coal in the fog was the model, and then the fog turned out to be the measurement. Part 12. 4 answers still standing. I have been telling this as though the black hole star model won. It did not win. It is leading, which is a different thing, and presenting it as settled would be a misrepresentation of a field that is still actively arguing. There are at least 3 other serious proposals being defended in peer-reviewed journals, using the same data, in some cases by some of the same researchers, and the newest of them is the reason this video exists now rather than a year ago. The first alternative reaches further back into cosmic history than the black hole star model does. Devesh Nandal at the University of Virginia and Abraham Loeb at Harvard published a first principles investigation in the Astrophysical Journal in February 2026, asking a simple question. What if these are not black holes at all, but stars? Specifically, the universe's very first generation of stars in a form nobody has ever directly seen. Population 3 is the name astronomers give to that first generation. They formed out of pristine hydrogen and helium before any heavier element existed anywhere, because there had not yet been a star to make one. Theory predicts they were nothing like the Sun. Without heavier elements, gas cools inefficiently, and inefficient cooling means the clumps that collapse into stars are enormous. Population 3 stars are expected to have been hundreds, thousands, possibly hundreds of thousands of times the mass of our Sun, and correspondingly short-lived, burning through their fuel in a few million years and then collapsing. Nandal and Loeb showed that supermassive stars of around 1 million solar masses match the observed luminosities of the little red dots, and that an extended stellar photosphere, a puffed-out outer layer, around such a star can reproduce the V-shaped Balmer break. Notice how close that is to the black hole star picture. Both say, a dense gas surface, radiating like a stellar atmosphere, hiding whatever is inside. They disagree about what is inside. One says a black hole, The other says a star so massive that it is about to become one. And then, in July of 2026, Nandel and collaborators published the result that makes this current. Because there was a hole in everybody's model, and nobody had filled it. Every version of this story, the black hole star, the supermassive star, all of it, requires dense gas wrapped tightly around the source. That is the whole mechanism. But where does the cocoon come from? Nobody had a way of making one. It was being assumed rather than explained. Their answer is that the star makes it, and the way it makes it is extraordinary. The team ran 5 stellar evolution models using GENIC, one of the standard codes for modelling the insides of massive stars, pushed here far outside the regime it was written for, onto objects of order 100,000 solar masses. They followed those models through their late evolution and applied radial pulsation calculations and general relativistic stability diagnostics. That last phrase is doing real work. At these masses, gravity itself begins to destabilize the star, so you cannot model it with ordinary physics. What they found is that the mass loss in the final stages does not happen the way it does in ordinary stars. Massive stars normally shed material through a steady wind, a continuous outflow blown off by radiation pressure over hundreds of thousands of years. This does not do that. This happens in bursts. The star becomes pulsationally unstable, specifically through something called a strange mode, which is a real and named class of instability that shows up in stars where radiation pressure dominates over gas pressure. Strange modes grow on dynamical timescales rather than thermal ones, which means they develop fast, and when they let go all at once. So picture it. A star of 100,000 solar masses, made of essentially nothing but hydrogen and helium, because nothing else has been invented yet. So massive that its own gravity is bending the rules of its own stability, and so bright that the light inside it is pushing outward harder than the gases. It begins to pulse, not gently. 4 times, in its final stretch it heaves. Each heave lasts somewhere between 41 and 282 years, which sounds long until you remember that this is a star, and stars measure their lives in millions. 4 convulsions, spread across a handful of centuries, and each one throws off somewhere between 10 and 348 solar masses of material. And the last one is the big one. The final episode alone accounts for roughly 73% of everything the star will ever lose. A last breath, larger than all the others combined. Then the star, having built its own shroud out of its own body, collapses inside it. If that is what a little red dot is, then what we have been photographing is a supermassive star's deathbed, wrapped in the last thing it exhaled, on its way to becoming one of the first black holes in the universe. And there is something worth pausing on in that possibility, quite apart from the little red dot question. Population 3 stars have never been observed, not once. Every statement anybody has ever made about the first generation of stars is theoretical, inferred from what the physics of pristine gas ought to do, and from the chemical fingerprints those stars left behind in the next generation. They are one of the great missing pieces of observational astronomy. If the little red dots turn out to be supermassive population 3 stars, then these unremarkable red specks in the corners of deep field images would be the first direct sighting of the first stars in the universe. That would be an extraordinary result entirely on its own, independent of anything to do with black holes. The second alternative comes at the problem through simulation, rather than through stellar physics. A team led by Kensi ran high-resolution radiation hydrodynamic simulations of the early universe, and proposed that the dots are direct collapse black hole nurseries. Direct collapse is a shortcut. The standard route to making a black hole requires a star to form, live out its life, run out of fuel, and have its core collapse. Direct collapse skips all of it. Under particular conditions in the early universe, you need to suppress the molecular hydrogen that would normally let a gas cloud cool and fragment into ordinary stars, typically by having a bright neighbour flooding the region with the right kind of ultraviolet light. A large cloud of pristine gas can collapse straight into a black hole, with no stellar stage at all. Their simulations reproduce the observed emission features, the abundance, and the compactness. A separate paper in February 2026, led by John and Brom and collaborators, reaches a compatible conclusion by a different route. The third alternative does not look at the black holes or the stars, it looks at the scaffolding. Nearly every galaxy sits inside a halo of dark matter, and those halos rotate. They inherit their spin from tidal interactions during their formation, and the amount of spin varies from halo to halo, in a well-characterized distribution. Fabio Pacucci and Abraham Loeb at the Harvard-Smithsonian Center for Astrophysics proposed in August 2025 that the little red dots come from halos in the extreme low-spin tail of that distribution. A halo that barely rotates cannot support a wide disk. Gas falling in has no angular momentum to speak of, so instead of settling into orbit at a comfortable radius, it goes straight to the center. The result is matter concentrated into a small, dense, brilliantly glowing core. Low-spin halos tend to concentrate mass in the center, Pacucci said, which makes it easier for a black hole to accrete matter or for stars to form rapidly. What I find compelling about that model is its economy. It explains three separate observations at once: how many of these things there are, how small they are, and when in cosmic history they appear. And it does it without inventing any new physics. In their picture, the dots are not strange because the physics is strange. They are strange because they live in rare places. And I want to point out something about that list of 4 explanations that is easy to miss. 2 of them, the supermassive star model and the low-spin halo model, share an author. Abraham Loeb is arguing more than one side of this. That is not inconsistency. It is what a genuinely open question looks like when a serious person is working on it. You do not commit to an answer and defend it. You develop the strongest version of each possibility and see which one survives contact with the next dataset. The field itself has noticed the shift. A review published in 2026 surveys the whole landscape under the framing "The Assembly of Early Supermassive Black Holes in the JWST Era," which tells you that the question has quietly changed shape. It is no longer, what on earth are these things? It is, how do these things fit into the story of how black holes got built? That is progress, even without an answer. Before we go to the end, I want to deal briefly with a claim you may have encountered, because it's circulated widely and it deserves a straight answer rather than a sneer. The claim is that Webb disproved the Big Bang. It spread on the back of the Impossible Galaxies headlines in 2023, usually attached to one of 2 alternatives: tired light, where redshift is caused by photons losing energy over long journeys rather than by expanding space, or a cosmology with varying constants in which the universe is roughly twice as old as we think. The answer is that the age of the universe is not derived from galaxy formation timelines at all. It rests on 4 independent pillars: the cosmic microwave background and the detailed structure of its temperature fluctuations, the abundances of the light elements produced in the first few minutes, the large-scale distribution of galaxies, including a characteristic scale frozen into it from sound waves in the early plasma, and the distance-redshift relation measured with supernovae. A surprise in how early structure assembles revises astrophysics. It does not touch the expansion history, and none of the alternative models reproduces the microwave background spectrum, which is the most precisely measured black-body radiation in nature. There is a quieter fact worth adding. This story has resolved largely in favour of the standard model, not against it. The masses came down, the tension eased. What needed revising was not cosmology. It was a measurement habit, which is less dramatic than the headline and considerably more unsettling. Part 13. These are not galaxies. So let me finally answer the question this video opened with, and let me answer it honestly, including the parts that are less comfortable than the headline version. You've probably heard, at some point in the last few years, that Webb found galaxies older than the universe. It did not. Nothing in the sky is older than the universe. Not a galaxy, not a star, not a dot. That claim was never made in any paper, and it never could be, because the age of the universe is not a number derived from looking at galaxies. It comes from the microwave background and the light elements and the expansion history, and those measurements are independent of anything a telescope sees in a deep field. What was actually found is stranger than the headline, and it took 4 years to say clearly. Webb found several hundred objects in the first 1.5 billion years of cosmic time that looked far more massive, far more mature, and far more compact than the available time should allow. And every category we had for them turned out to be the wrong shape. They are not old evolved galaxies. The density argument closes that door from both sides. They are not dust-cloaked feeding black holes. The X-rays, the warm dust, the radio and the flicker all say no. The leading model says they are not galaxies at all. They are single objects, compact, enormous, and enclosed. A black hole, or possibly a supermassive star about to become one, wrapped in an opaque envelope of hydrogen and radiating from the outer skin of it, the way a star radiates from a photosphere. Not a system of billions of stars. One thing, wearing a surface. That is the finding, and it is the reason the thumbnail on this video says what it says. These are not galaxies. But that is not the part that should keep you up, and I have been building toward the part that should for 2 hours. Nobody has ever visited a galaxy. I said that earlier and let it pass, and now I want to put weight on it. Nobody has ever been to one. Nobody has ever measured one directly. Every single number ever published about any object outside our immediate cosmic neighborhood, its size, its mass, its age, its composition, its distance, the speed of the gas inside it, is an inference. Here is the chain, and it is worth walking slowly, because I want you to see how sound it is. Photons arrive. Some very small number of them, after 13 billion years in transit, land on a detector. They are counted. They are sorted by wavelength into a spectrum. That spectrum is compared against a library of models. Models built from physics we understand extremely well and calibrated against objects we can study closely. The model that fits best is identified, and then the parameters of that model are written down and reported as the properties of the object. Every step in that chain is sound. Every step has been tested against thousands of known sources. Every step is the accumulated result of a century and a half of careful work by people who are checking each other constantly. And every step contains an assumption that is correct nearly everywhere it has ever been applied. The little red dots broke the chain in 2 places at once, and they did it quietly. A Balmer break was read as age, because a Balmer break means age, in every galaxy anybody had ever measured. Here it may have meant density. A broad emission line was read as orbital speed, because a broad line means speed, in every accreting system anybody had ever weighed. Here it may have meant a fog. Neither reading was careless. Both are the correct default. Both are what you should do, and what a good astronomer would do, and what you or I would do if we sat down with the data and the standard tools. And applied to an object with no local analogue, they produced numbers that were wrong by a factor of 100. And those numbers went out into the world and were believed by everybody for 3 years, including by the people who eventually corrected them. I want to put that in the plainest terms I can, because it is easy to nod at and hard to actually feel. Imagine you are handed a photograph of an object nobody has ever seen before, and you are asked how heavy it is. You cannot pick it up, you cannot go there, you can only look. So you compare it against every object you have ever weighed, find the one it most resembles, and reason from there. That is not a bad method. It is the only method. And it works right up until the moment you're handed a photograph of something that resembles a thing it is not. There is no alarm that goes off at that moment. The comparison still returns a match. The arithmetic still produces a number. The number still has error bars, and the error bars are still honestly computed, and they are still far too small, because they describe the uncertainty inside the assumption rather than the uncertainty of the assumption. So here is the terrifying part, and it is not out there. It is not that the universe made something inexplicable. The universe is entitled to do that, and frankly, it is what we point telescopes at it for. It is not that cosmology broke, because cosmology did not break. It came out of this stronger, not weaker. The terrifying part is that a category error of that size was sitting in plain view, in the most scrutinized dataset in the history of astronomy, examined continuously by hundreds of the best-equipped people who have ever lived, and it took 4 years to find. And the only reason it was found at all is that those same people kept trying to break their own best answer, published every null result, and told everybody when they failed. That is the system working. I want to be clear about that, because it would be easy to take the wrong lesson here. Nobody hid anything. Nobody was pressured into a conclusion. The correction came from inside the field, in public, in journals anybody can read, submitted by people whose own earlier papers were the ones being revised. Ivo Labé's name is on the 2023 paper that started the panic, and it is also on one of the 2025 papers that took it apart. And there is a version of the popular framing that turns out to be right after all, just not in the way it is usually meant. The way people put it is that if these objects are real, then either the universe is not the beginning of everything, or our understanding of how galaxies form is plain wrong. The first option was never on the table, but the second one is, in a modest and specific sense, true. Our understanding of how the earlier structures assembled did need revising, and it was revised. Not overturned, not replaced. Extended to include a kind of object we did not know could exist. One where a black hole grows inside its own food supply, or a star hundreds of thousands of times the mass of the sun builds its own tomb out of its own body and then climbs inside. That is a real revision. It just is not the apocalyptic one, and I think the real one is more interesting because you can hold it in your hand. But the system working is not the same as the system being finished, and the honest question that this whole episode leaves behind is not about little red dots at all. There is a picture you have almost certainly seen, a black field crowded with light, thousands of galaxies at once. You have looked at it and felt something. Most people do. Look at it again and find one of the small ones. A red speck, 4 or 5 pixels across, the kind of thing your eye slides past on the way to the pretty spiral in the corner. That speck is a number of counts in a detector. Those counts were sorted into a spectrum. That spectrum was compared against models built from stars we can see nearby. The closest match was chosen, and the parameters of that match were written down and published as the age and the mass and the size of an object 13 billion light-years away. Every link in that chain is sound. Every link contains an assumption, and nobody has ever seen anything else. That is all we have ever had. 4 pixels, and a very good set of rules for turning 4 pixels into a sentence. I do not think that should make you trust the sentences less. If anything, it should make you admire them more, because the remarkable thing is not that one of them turned out to be wrong. The remarkable thing is how many of them are right. We built a picture of a universe we can never visit, out of the faintest possible signal, and most of it holds. That is not a small achievement. It might be the largest one our species has managed. But it does mean the sentences are provisional in a way that the confident tone of them does not convey. They are the best current reading of the light, not the object. So the last thing I want to leave you with is not an answer. It is the question that 4 years of this has quietly opened, and nobody in the field has closed it. If an error of 2 orders of magnitude could hide in the best data we have ever taken, watched by the best people we have for years, then somewhere in the catalogue, in among all the confident numbers about all the distant things, how many of them are measurements of the fog? Sleep well.